kilowatts. That probably warrants a pretty detailed look. So have something on that point right at the end of the workshop. So I'll just leave that teaser out there, and I'll try to remember to share when we get back to that point. How are we doing on numbers, Jay? As in, should we wait here a couple more minutes?
No, I think let's dive into it.
Okay, excellent. Then let me do that. So, as I mentioned, if you were here, today's webinar is on estimating project savings. This particular webinar is focusing on pump and fan systems. So my name is Nick Dial. I'm an energy coach at Wolfen, and I'm excited to be here talking about this. I've been working on pump and fan system energy savings since my very first job out of university, that is. And that's actually where I met Vern Martin, a storied expert on fans, who is going to be my co-facilitator here today. So I'm going to be taking us through the training proportion of today's webinar, and Vern is going to lead the Q&A in the second half. Vern, do you just want to say hi?
Hey, can you hear me okay?
You bet.
All right, perfect. Good to be here and nice to see the group here. Is my video working okay, Nick? All of a sudden I got a thing that flashed up, said it's not working.
How's it look, Jay? I can't see people's
It's a
faces
little bit
anymore.
frozen at the minute, so maybe try turning that off and back on, but the audio is fine.
Okay, good. All right.
That's a great time to mention this training is going to be recorded, and it, along with other training materials, will be available on the new training and support page of the Save on Energy website. There should be a link in the chat if you're interested. That should be arriving there right about now. Okay, before we get going, just a reminder to download or print your participant workbook. It includes a lot of useful additional information to what you're going to see on the slides here today. You can get that from the calendar invitation for this event, or it also should be in the chat window right about now. And before we get going, I'd like to introduce Vicki Gagnon from the IESO to talk for a minute about some some retrofit program updates.
Yep. Hi, I'm Vicki Gagnon with the IESO. I work on business programs in demand-side management, working primarily with public sector organizations. And we are pleased that you're interested in using data to drive savings in your facility. And we have a very full webinar planned. So before we get started, I want to tell you about the Save on Energy fall retrofit updates that were announced last week. Prescriptive incentives for most non-lighting measures have increased as of yesterday, October 30th. Most incentives have doubled, and some have increased 3 or 4 times, including for air source heat pumps. So in relation to today, pumps, fans, motors, most non-lighting prescriptive measures have increased, have doubled. And secondly, the last day to apply for lighting projects in retrofit, both prescriptive and custom track, is December 17th. And the instant discounts program for lighting launches December 18th. And in that program, incentives are paid directly to distributors, enabling them to offer instant point of sale discounts on energy efficient lighting, so that you can purchase already discounted lighting from participating distributors without any paperwork on the part of the customer. And you can find more information on all of these changes on the Save on Energy website. And with that, I'll turn it back over to Nick and Vern.
Great. Thank you, Vicki. All right. So today's webinar, the training portion of today's webinar is going to follow a 3-point agenda, starting with pump and fan fundamentals, including types of pumps and fans, pump and fan curves, basic principles and equations for understanding pump and fan operation. Then we're going to move into the estimating pump and fan energy baselines. This will include some more equations for calculating power and incorporating load and duty factors when developing your energy baselines. And then we'll move into estimating pump and fan project savings. including a look at the fundamental mechanisms of savings behind these projects with pumps and fans, typical opportunities and solutions, as well as calculation pitfalls to avoid. After that, we'll move into the Q&A with Vern Martin. So understanding some pump and fan fundamentals is critical to understanding how to calculate energy savings. But the expectation of this audience here today is that you know these fundamentals. So this first part is intended to be a refresher, and it's going to move pretty quick. The participant workbooks have some additional materials as well as additional references. So if some of this material is new to you or newer, please check out that referenced material. It's some of my favorite go-tos over the years. If you have questions about the fundamentals that we're covering here today, that's fair game. Feel free to put up your hand or put a question in the chat. However, if you have a more detailed question about pump or fan systems more detailed question or something you don't see in the materials, please save that to the Q&A. We're happy to get into those details. That's why we brought a fan expert here who also happens to know quite a bit about pumps. So we can answer those questions there in the Q&A. All right, now to what's on the slide here. So starting with pumps and most specifically the pump curve. The pump curve is the relationship between flow and pressure or head for a given pump or fan. What's not shown on this pump curve, but is included with most pump curves, would be the associated power curve. Pumps break out into two main types. You have rotodynamic pumps and positive displacement pumps. Today's material is mostly going to be applicable to rotodynamic and more specifically centrifugal pumps. That is because these are the most common pumps, and this is where most of the energy savings opportunities lie. Here you can see the pump equation or the pump power equation. We've got the metric and imperial equation shown here. These are also in the participant workbook. This can be simplified, when dealing with water in particular. You can see kind of the simpler version of the equation here. The important takeaway is to understand the relationship between flow, pressure, pump efficiency, and power. So you can see what's on the top of the equation, flow and pressure, divided by that efficiency. This will become relevant or important when we talk about how to improve the efficiency of systems or how to save energy, as well as how to calculate them. Moving on to fans, this image here shows us how different the different types of fans are.
Hey, Kevin.
So pictured are 5 types of fans, ranging from high pressure, low volume with radial blades centrifugal to the other end of the spectrum with ducted propeller fans, high volume, high airflow, low pressure. All the content we're covering here today is applicable to all these fan types. Similar to the pump equation, we have a fan power equation. Same basic idea here. You have the relationship as your flow times the change in pressure over efficiency is what gives you your fan power, and that'll become more relevant as we get into these savings calculations. So those are the types of fans and pumps. Now we need to, we're going to move on to talking about the systems in which they operate. So a pump or fan will always operate at the intersection of the pump or fan curve and the system curve. The system curve is the relationship between pressure and flow, including the static pressure or lift, as well as the friction generated by pipes or ducts and any restrictions as the flow increases. The system is going to look different if you have different, for each different system, and if you have a fixed resistance system versus a fixed flow or a fixed pressure system. Again, I'm going to refer you to your participant workbook. If this is new content for you, I've referenced a couple of good guidebooks that were developed or sponsored by the IESO, as well as other utilities across Canada, that break this down to some good fundamental levels, fundamental level with plenty of illustrations so that these concepts can be quickly grasped. I'm sure most of you are familiar with this equation. This is saying that for some pump and fan systems, power is proportional to speed or flow cubed. This can be a very handy calculation, but it must be used with caution. So when not to use this equation is, for starters, with positive displacement pumps. This would not apply. It's also not applicable to systems with high static head. You can see that on the image on the right, where as the top curve is showing you a system with high static head versus the system that is a fixed resistance, purely frictional system, where that being the classic example where the linear fan laws would apply. As you move up and down that system curve, you could use the affinity laws, this cubic relationship, to calculate the impact on the brake horsepower, the mechanical power of the system as the speed increases or decreases. But that's, one other thing to keep in mind when you're using this equation is you need to be on the same system curve. So if you're moving from a system controlled by a damper or a valve to one without, you're likely changing not just the operating speed, but the system curve. So be cautious. And also don't forget, this is talking about your output power, your mechanical power. So you need to factor for your motor efficiency, the drive efficiency itself. So if you get into the low loads in particular, if you're reducing your speed down to about 40%, this could be a factor in terms of what is your motor efficiency or your drive efficiency once your motor is so lightly loaded. Okay. I'm going to pause here, see if there's any questions. I haven't seen any hands raised, but we're wrapping up the pump and fan fundamentals. Like I said, it was going to be quick. And we're going to switch over to the motor side of pump and fan systems in a moment.
There is a question about how would high-speed turbo blowers fit into this?
It's a good question. I'll start and then maybe refer to Vern, which is to say that you may be getting into a compressible fluid, into the compressible range. So if I back up real quick, these equations apply, if you're staying roughly below 20 inches water gauge and assuming compressibility is not a factor. Once you're getting into turbo blowers, I believe compressibility is a factor. Vern, I don't know if you could confirm that, but if it is, then there is still a equation for that, but you need to be factoring for the air compression in that calculation.
I think you said it about exactly right. I would perhaps add to that turbo blowers don't behave that much differently than any other kind of high speed, high pressure fan, but there definitely is a consideration there that all of a sudden compressibility starts to become a more of a major factor. It always is a factor, but at under 20 inches water gauge, we normally disregard it just because the impact of compressibility is not that significant. Above that, you do have to take it into consideration. You have to remember that fans and blowers are thermodynamic machines in a sense, and of course you have a lot of heat that gets generated once you start to compress flow, and so that is a factor. And beyond that, I think you'd have to look at the specifics of what equipment it is you're referring to.
That's great. All right. Do you have any other questions we should address now?
Nope, that's all that's come up so far.
Right.
Nick, can I just jump in on one point here about the affinity laws, and it really is a comment concerning pump affinity laws. They work quite well. It does need to be kept in mind that pump affinity laws, generally they're separated into two different types. There's ones that affect making changes within an existing pump, and then there's another one that has to do with the whole pump having changed. So for example, the pump affinity laws also have an impact on the diameter, and when you're comparing a diameter change within an existing pump housing compared to a diameter change where you're also changing the housing to be larger or smaller, those affinity laws will change. So that's a caveat that I wanted to add to that slide.
It's a good additional caution. Thanks, Brent. Okay, so moving into establishing pump and fan system baselines, the premise of today's workshop is about helping you to estimate savings for potential projects when you have imperfect information, to assess whether to invest more time and resources into a project. So wanted to ask here, and get your fingers ready to hit the chat or put up quickly about, so we're curious to hear, what data do you usually have available? So if you're looking at a pump or fan system of interest, just use the chat, is probably the best way to do this. What data do you usually have on hand, or can you get? And I suppose if you have three-phase power on every pump and fan in your facility, you needn't mention that because that'll probably just annoy your colleagues here.
Yeah, let me see. Nameplate info has come up in the chat. That's a pretty common one and a good starting point that I think most people are able to get.
Right. Yeah. Okay. Please keep keep sharing, but that's a great segue to where we're going to start here. So if you've got nothing basically other than a nameplate, this is where you can start. So you can see the equation on the screen here for how to take that nameplate and calculate power in kilowatts, or to turn that into an energy baseline once you add the element of time, your annual hours here. The two key things I would raise your attention or consider here is those two letters LF, load factor. So that's kind of a catch-all uncertainty if you're estimating from the nameplate. So you can either make it up based on a rough guess, 75% load factor, but I think it's a good practice. Maybe you've previously measured similar systems, so you have an idea of where this system operates. Vern was talking to me just as we were preparing about just observing the motor. That is it warm? That's a good indicator that it's running pretty well loaded. So the load factor is the big uncertainty there in terms of converting that nameplate into a power estimate. Also, I'll mention, as the box at the bottom alludes, this would give you your mechanical power. If you wanted your electrical, your input power, you need to factor the motor efficiency as well. Okay, going to move from there into the three-phase power equation. I think the equipment we're talking about that you're looking at in your facilities is mostly going to be three-phase power, and that's going to be where the significant energy savings are. The handout that you have gives a couple methods for calculating power using the three-phase power equation. I guess I should back up and say that often what is, if not readily available, feasible to collect is our amp or current measurements. So that's a great place to start. If you have a load measurement, then you can use the three-phase power equation to get a pretty reliable power estimate. There are a few things you want to keep in mind. So, the voltage is hopefully close to the line voltage or rated voltage. Power factor, as long as you're above, half loaded on that motor, you can pretty reliably estimate the power factor as well. And that's going to lead you to reliable power estimate. As I mentioned, the handout has a couple of methods for working with a amp or load measurement to come up with a power estimate. Okay, so moving on to calculating baseline. So here we're introducing the element of time. If you take one thing from today's session, let it be this: you can't accurately estimate your savings if you don't have an accurate baseline. In my experience, about 90% of underperforming energy savings projects are because of an overestimated baseline. So a couple quick tips on making sure that you don't fall into this trap. So we've talked about how to calculate power. You can use that three-phase power equation, or maybe you've got power, or even the nameplate factor. We also covered the pump and fan equations and spoke about fan curves. Those are great ways to do a check of your power estimate, do a sanity check to see if it makes sense based on the pump or fan equation, or looking at your pump or fan curve. So try to check your power estimates, check the sanity of those before moving forward. When introducing the element of time, this is often where things go awry. So I've seen a lot of baselines and energy savings estimates that overestimate the amount of time that a system is running, or the amount of time that it's running a certain mode. So make sure to consider the operating modes of the system, as well as the duty cycle for your system, to really get an accurate assessment of how long or how often your system is running. While power measurements might be hard to come by, there is often within a system some good operating data that can serve as a proxy for the operating modes or the duty cycle of your system. As I mentioned, the handout includes some tips on how to calculate baseline, including walking through a couple of examples. All right, we're going to move into the fun part, getting into estimating savings for pump and fan systems. So the first thing I want to impress upon everyone is there's really only 3 ways to save energy with pump and fan systems. You can reduce flow, you can reduce pressure, or you can increase the efficiency. So we kind of alluded to this when we talked about the fan and pump equations. You have flow and pressure on top and efficiency on the bottom. That's it. That's how you calculate pump and fan power. So assuming you're not going to change the density of your fluid you're pumping, it's got to be one of these 3 things or multiple. So starting with reducing flow. So the mechanism here is moving less volume. So this could include turning pumps or fans down, as in reducing flow, or turning them off when not needed. So that's kind of my cheat way of introducing the 4th way to save energy, which is the element of time. Don't run them, or turn the flow down to 0, you might say. So solutions that reduce flow include eliminating a bypass or eliminating excess flow by right-sizing your system, or by introducing a VFD. Other options are on-off controls, as we suggested, or a big one is just to reduce or eliminate leaks. In terms of calculation pitfalls, I'll go back to an image we used with the affinity laws earlier. And as we mentioned, if you have a system like the one on the right, your affinity laws are good at predicting this, predicting these savings. However, if you have a system like the one on the left, or the top, I suppose, with a high static head, the affinity laws are not applicable. But also just important to know that reducing flow in general won't have the same impact in terms of energy savings, because a lot of the energy is being used just to lift the fluid to where it needs to go. Reducing pressure, the mechanism of savings behind, in terms of reducing pressure would be reducing restrictions that are imposed on the system and the fluid that you're moving. So this, those restrictions could be dampers, valves, bends, the pipe length or run, could include reducing your height or your head differentials in open systems. So I've heard of and seen examples where liquids are just being pumped to higher heights than they need to be, or exiting pipes where you could pipe it in at a lower height. Just a quick change of exit could save some energy. So solutions for reducing pressure include VFDs to eliminate that damper or throttling, increasing your pipe or ducting diameter to reduce restrictions, and improving maintenance practices that are imposing greater restrictions, particularly over time. Calculation pitfalls, applying the affinity loves for a system. We kind of talked about this for different system curves. So if you're reducing the amount of restriction, you're actually changing the system curve, and you can't use the affinity law to estimate what what those savings would be. All right, finally, increasing efficiency. So the savings mechanisms here, really, we're just talking about operating at the best efficiency point, which I'd say most systems, if you were to look at them, are not. So they are either changed after being put into service, the system is modified and moved away from its best efficiency point, or the system was over-designed to begin with and never really operated at its best efficiency point and was perhaps throttled in order to achieve its design flow rate. The other option here is to install higher efficiency equipment, in kind of looking at that retrofit opportunity. The system may be operating okay, but you might just be able to put in more efficient equipment. So solutions here could include recommissioning or right sizing if all you're doing is improving the system efficiency. However, I think the big opportunity in terms of increasing efficiency is in combination with the two previous opportunities, particularly, well, really both, so that when you're improving the design of a system or the operation of the system to save energy, when you're reducing flow or reducing pressure, you also likely have the opportunity to move that, like if you're not replacing the pump or fan itself, but to have an opportunity to move towards the best efficiency point as opposed to away from it. And it should be said with VFDs that you can, as you reduce the speed, the efficiency should be maintained up to a certain point. And so the idea would be to increase or reduce speed on that line. And you can see it on this curve here. You can see these ISO lines that represent, consistent efficiency, and you can reduce the speed along that ISO line to maintain efficiency as you reduce the flow. The point that kind of leads me to is a calculation pitfall is not factoring for changes in efficiency while reducing flow or while reducing pressure. So as I said, the impact of efficiency is often in combination with one of the other two changes. Okay, bit of a busy slide, but just wanted to kind of bring it home with a worked example here. So on the left, you can see a pump curve and as well as a system curve. And in this case, in addition to the pump curve, we have the power curves at the bottom. So there's 3 curves in each representing different speeds. You can also see these ISO lines that I mentioned. So the starting point operating is between the 83 and the 86% efficiency points and is at the 1480 revolution per minute speed. And this project proposes to reduce the flow from around 700 meters cubed per hour to between 400 and 500 meters cubed per hour. So the method for calculating these savings, kind of following the practices that we've discussed, like we have a very useful curve here. So we can go from that operating point down to the power curve, over to the axis for power to interpolate and say that's about 110 kilowatts. We can also use the pump equation. So this is displayed on the right side here, and that gives us about, well, a very accurate 105.8 kilowatts. So pretty close to my interpolation of about 110 kilowatts. Important thing to remember here is we're talking about mechanical power. If we want to convert that to electrical power, we need to factor for the motor efficiency. So that's what we've done with an assumed 94% motor efficiency to get 112 kilowatts. Next, I want to look at what the post-project or the impact of the project power would be. So let's look at that second operating point. We're now at the lower speed curve. So take that line all the way down to the middle curve there, bring that over, and that brings us to about 70 kilowatts, as is shown on the right as well with the equation. We can use the motor efficiency. We degraded it by 1 point. We're now at a slower operating speed. It might be negligible, but just for the point of demonstration, we changed that efficiency a little to end up at 76 kilowatts. This is important or an opportune time to mention that had I used the affinity calculations, I would have got a post-project power of about half that, of about 32 kilowatts. So this is showing you the impact that the static head has on that and why we can't assume to use the affinity laws. So to arrive at a power reduction, we just need to take the baseline power, 112 kilowatts, subtract the 76 kilowatts to arrive at a 36.5 kilowatt power reduction. Not bad. I'd do this project. All right. We're going to wrap up, and then we're going to move over to Vern for the Q&A. So just in wrapping up, wanted to talk about methods, which, the first reminder, I guess, or tip I want to leave you with is the suggestion to combine calculation approaches to establish the baseline power estimates. One on its own is maybe not too reliable. Even the pump or fan curve, you might think that this is, dogma for this pump or fan and is fact, but in fact, there's lots of reasons those curves can change over time. So combine methods to validate your calculations. Secondly, always assess the duty cycle when developing the energy baseline, and that could say the load factor or operating modes and duty cycle. So to make sure that you understand how this system operates over the course of the year and don't overestimate your energy baseline. And then finally, as we just did in that worked example, always start from your baseline when estimating your savings. You can calculate the baseline and then a separate power post-project calculation, as we did there, or post-project power, or you can just apply a % reduction from the baseline. But the point is, establish your baseline before coming up with a savings estimate if you want to estimate savings accurately. On the tool side of things, and if you're using software tools, especially to help estimate these savings, we'd always recommend that you make sure you understand the system first and don't blindly input things into a calculator and trust the result. We would always suggest that you consider doing your own calculations. I think one of the points of this presentation or objectives was to show that these aren't very complicated equations, and the mechanisms of savings behind these projects are also not that complicated. So we'd encourage you to try to do these calculations yourself, and that way you will understand more about the system or understand the results that you're getting. And then, yeah, in general, just be cautious with any calculators or tools, and particularly if using the fan or affinity laws.
Thanks,
With that,
Nick. And
go ahead, Jim.
yeah, we're going to go into the Q&A. So there is a Q&A option in Teams at the top. If you have any questions for Vern, you can either raise your hand and then we'll call on you to unmute yourself, or you can type them into the Q&A and we'll bring them up. While we're waiting for people to do so, I had a question. Like a large part, I think there's a very good point made of like the first step is understanding your system and your baseline and how that's going to be done, and the use of the pump and the system curve. So I think one of the questions that I would have about there is, if someone's starting out and they have limited information, how would they get those curves, the pump and the system curve, to start understanding where they are and what changes will have, what impact changes will have?
Jay, I think that question's probably for me.
Yeah.
So you raised a great point, and I tell people with projects that we work on to treat their curves like gold, make sure they've put them away properly in their engineering files and keep them. Having said that, it's definitely the case that many people do not treat their curves in that way. So then you're into workarounds for this. So what are the workarounds? The workarounds, if you're dealing with catalog fans, is to get onto that nameplate and see if you can't find the fan manufacturer, the pump manufacturer, and do a search to see what you can find by way of curves. And then once you get that, and again, you got to go back to the nameplate. Quite often the flow and the pressure and the power for the design point is listed on there, and you should be able to correlate that with a curve. Now, it's also the case that many of these manufacturers come and go. And so if you're dealing with a fan or pump that's 30 years old, you may have some difficulty, or perhaps much older than that. You might have difficulty in finding it. So now you're into looking to see what other competitors there might be that have similar equipment, and whether or not you correlate to one of their curves. But you know, it's sometimes it's a hunt. You're on a hunt here to get hold of this stuff. I can offer a few other suggestions, at least not so much with pumps, because we're more fan specialists than pump specialists. But you know, we may be able to recreate a curve based on the compendium of curves that we've stored over the years. So if I know the diameter, I know the width, I know the design of the equipment, then chances are we may be able to recreate it. But and then if you really wanted to get complicated and turn it into a real science project, then we could maybe use computational fluid dynamics to actually recreate it. I'm not suggesting that, by the way, because this starts to get into a very expensive process. And if somebody calls you up and you've got a 20 horsepower fan, that embarking on a $20,000 or $30,000 CFD exercise isn't warranted. I can tell you that. So I would use one of the other workarounds first before I get to that point. But I will say this. I'm sorry, I'm going to have to make a slight plug here. But we've been doing fan and pump work for 30 years. And over those years, we've tested a lot of fans and a lot of fan manufacturers that no longer exist anymore. So if you called me up and said, I got this fan out here like this, I might not have that curve, but Nick has alluded to the affinity laws. So with the affinity laws, I may be able to recreate it that way. And that actually is a fairly inexpensive exercise to do it that way.
And what about the system curves on that? How would one get an understanding of what that looks like for their particular system?
So that is a bit more of a complicated one. first of all, we talk about the system curves, but when a system is designed, quite often the engineers that put that together don't talk so much about the system curves as they just simply talk about what the system operating point is, or the system operating points are, and then you have to kind of work it back from there. The only real way to know what a system curve looks like is to collect some data on the system as it exists on site. And that means knowing what the flow is, knowing what the pressure is, and then knowing what it is if you're making changes to the system. So for example, if you've got let's take a simple example, which is an HVAC system. And let's say the HVAC system, over the course of the day, it backs off because temperature is satisfied, or when it comes on in the morning and all of a sudden you have to have the sun comes up and hitting the side of a building, you got to crank up your HVAC system. So you got a series of points that you're collecting at that point. So that is, in essence, how you would develop a system curve, by knowing what the low points are, or knowing what the high points are, and having some idea of how you get from one to the other. If you're closing a damper down and so on, then that is part of that methodology there. Knowing what the delta P is across that one element in your system that's changing. If you got a damper that's changing and you got a pressure upstream and a pressure downstream, then it may be that the rest of the system is all fixed elements, which doesn't really change. But that one element in there may change, and you'd have to have some idea of what that is. And the only real way to know what that is to measure it, and maybe monitor it if you've got monitoring equipment you can put on it.
Mm-hmm. Okay. And we have a question from Darren in the Q&A about, would you recommend a seasonal check, like summer, winter, shoulder measurement set, to account for BAS changes? Like you mentioned, like changes in the system. So if there's seasonal changes due to BAS set points, does it make sense to do those seasonal checks? So like, in some instances, there may be makeup air versus no or less makeup air in the system.
So the question relates to understanding your load duty cycle, I think, and maybe that is a question that refers to HVAC systems, which really are a seasonal kind of thing because of the obvious change in the outdoor temperature and so on. But it also can be a question that affects other systems as well. And so here's the problem with this, is that when you're set out to do an evaluation on a system, you don't want to wait for 1 year to have all the data. And that's a bit of a problem. And so there's that very important logistical problem that enters into this. So now you're into studying it with certain things in mind as far as how they would change if the season would change. And in some industrial systems, it might not be the season so much. It may be something else that has to do with the raw materials that you're using or whatever else. But definitely when you do the evaluation of, and I think we're talking about estimating energy savings here. So we want to estimate energy savings. You have to know something about how your system is going to change over the course of the year to react to that. If it's simply reacting to a temperature change, then that's should be a fairly straightforward matter to calculate that. But the bottom line is that if you're going to estimate energy savings, you want to do it on an annual basis. And that means having some understanding of how the requirements, what the requirements that are being placed onto the fan or pump are going to change over the course of that year.
Okay, and Darren added a bit of clarification there. Darren, did you want to come off mute just so it doesn't get lost in my interpretation there? Or did Vern end up answering that?
Yeah, basically what I'm saying is that depending on the audience, you may actually have convoluted building automation systems, or you could have simple push-pull ducting systems, or straight up evacuation and just naturally infiltrated air makeup. But ultimately, you're going to configure your building between summer, winter, and shoulder season. So that means your fan curve for your optimum energy use is actually going to probably have 3 different settings. It's going to have a summer setting, and it's going to have a winter setting, and it's going to have a shoulder season setting. And your savings over the course of a year will actually be dependent upon what those various settings are. And if you don't actually do it, you're not squeezing the most out of your system. I'm saying that because that's what I run into in our bakeries. We actually have summer, winter settings, and we actually have shoulder season settings where we change the overall configuration of how the building is actually ventilated to control waste heat and humidity in the baking process. And I assume the same thing would actually be true in people operating everything from shopping malls to office towers. Like one set of settings will not be the settings for the year unless you have some underlying other criteria like humidity control or CO2 control that's actually going to do that. So ultimately what I'm saying is you can set the fan up for now, but now is not the entire year. Later in the year, right, the humidity is going to change, the outside air pressure is going to change, the evacuation rate you want inside the building, the specific air changes per hour you're going to want to do. I'm just pointing that out, saying that setting it once for the audience is not, it's a great start, but it's a start. And there's really, in my opinion, there's always 3 set points that you got to optimize your building for: summer, winter, and shoulder.
Yeah. Don't disagree with anything you just said there, Darren. I think you're absolutely spot on. And in the process of doing the energy evaluation, of course, you also have to go further and further away from the fans as well. But for example, if you're dealing with shoulder seasons, you don't need to have near the chillers running. You don't need to have a lot of other equipment running. So where you're dealing with in terms of the overall scope of how much the power and energy requirements are, they may change radically because you just simply don't need different equipment, or you need more of it or less of it depending on the time of the year that you're looking at. That all comes back to really understanding your system. I can't stress that point enough. Understand your system, know how these operating points will change as you go from one operating, we call them different seasons, but in a broader context, what they really are is different operating scenarios. They're different system curves possibly, and so on. And it may be the season and for one customer, and it may be something else for another. But bottom line is you have to know what those operating characteristics look like.
Great. Thanks, Vern. I think that's a really interesting point. One thing that I had, I was curious about is if people have different, so you've described like it can potentially get very complicated in terms of understanding your systems, particularly systems where that mode of operation does change throughout the year or throughout operations on there. Do you have any tips for if people are looking at projects and there are rules of thumb for different potential savings things, or those simple calculators out there? I think we talked a lot about today about limitations around those and ways that those may not be, but do you have any tips in terms of if someone has a project in mind of understanding, when that online calculator, the rule of thumb might be good enough for it to get a sense of, is this worthwhile, or when they really do need to put in that effort to really understand the system and get those more accurate estimates?
So let me answer your question this way, Jay, as far as how I treat this sort of thing, because that is one of my roles in the company. I get into some pretty detailed stuff, but I'm also the guy who gets invited out to take a look at a system sometimes with the basic question. I mean, is this worth looking at? What kind of rough numbers are there for making some energy reductions? And the very first thing I do, and Nick had it up on his slide before here, that there are only 3 ways to save power. Okay, that's all it is. Power is flow times pressure divided by efficiency. So you're going to have to make a change in one of those 3 areas. Now, let's deal with each one of those separately because there's some commonalities between them, but there are some differences. So with the flow on this, and this perhaps gets also to Darren's question or point here about the seasonality or the different settings of this system here, is just to take a look at this and try to get your mind wrapped around how much flow are we moving. And I don't mean that as an exact number, but are we, first of all, are we satisfying what the requirements are? And the, somebody in the building or in the particular process says, yes, we're satisfying that. And then you can look at it and say, okay, so how much of the time are we oversupplying this system, or how many operating points do we have where the system is oversupplied, and by how much? And so it all starts with that kind of a calculation. Remember, the very first and most important thing with any fan or pump system is to move flow. Okay, you got to move flow. That's what the thing was put in for. So now it comes down to a question of how much it really needs, or how much you can reduce it by. So then you start getting into making a few different assumptions on this, because if I look at a system out there and say, you know what, for a third of the time, I think we could drop the flow down by about 50%. Oh, well, that's some basic math here. So you can start come up with some estimates on what kind of reduction in power you should have. But there is an assumption with that, which is that for all of these different reduced points, you're still at the same efficiency. And that may or may not be the case, depending on how the control strategy gets you from this full flow condition down to some partial flow condition. Okay, but it's an estimate. Okay, so you got to start with an estimate, and then you can work through the different options and how you move from A to B, and still do that without sacrificing the efficiency. If you got to sacrifice efficiency, you may all of a sudden, or you don't have any options that allow you to keep the efficiency high, then you may not have a project, or the project you want. You may have a different project. So that's just dealing with the flow part of this. Dealing with the pressure side is almost the same thing, where you look at a system and it's very useful to walk through that system. And by the system, I'm talking about from the moment the flow enters into some hardware someplace and to the point where it's eventually exited, and being able to know what the pressures are at all points along the way. Now, that kind of data might not be all that available before you start into something. With the fan system, it's not so difficult. Punch a few holes here and there in the system and you take pressure readings, but you at least then are able to come up with a system profile of what does the pressure distribution look like as I walk through this whole system. And if you take a look at that and you can say, isn't that interesting? We went from this particular part of the system here to this part of the system here, and that represents, 50% of the pressure that these fans develop. What's with that? Does that make sense? Did I go through some particular process equipment or some hardware equipment there for which those losses are understandable? Or are you going to look at that and go, I don't understand why I've got 5 inches across these coils. That should be a half an inch water gauge across we must have dirty coils. They're plugged. They got to be steam cleaned. They got to be something. Okay. So this is also a very useful way to be able to come and actually it becomes part of a maintenance and a reliability program, as well as a study program for trying to figure out how you reduce energy. This is something also in the long term, but it all has to start with understanding something about what that pressure profile looks like, and where are you using the pressure? Where are the losses on this sort of thing? Mm-hmm. I'll give you an example on this, because I so often end up talking about fan systems instead of pump systems. But here's an example of one that I still love to this day, and it's a really old one that we did. But we got asked at a chemical plant to take a look at how to reduce power on this 250 horsepower pump that they had. And so you start off and you get a process and instrumentation diagram, and you start laying this thing out of, I think this part of the building gets this much flow and this part gets this much. And I'm looking at this thing going, I don't think this thing makes sense the way they're doing this. So it turned out that what was going on here was that they had a bunch of flow on the mostly all on what I would call the first floor of this plant. But there was one particular part of this system which was taking the flow up to the 4th floor. So all of a sudden, this pump needed to develop at least enough pressure there to get it up to the 4th floor. But the problem was it didn't hardly need much flow up there. It just needed the pressure to get it there. So now all of a sudden you got this pump, which is sized to develop a lot higher pressure than what is really needed for 95% of the system, all because there was this one part of the system that had this one particular need. And that often is the case that you run into, where you end up with either fan or pump systems, which have got multiple uses. Okay, you're trying to have a, you know, something that fits every need in a facility, that and all of a sudden, before you know it, that one particular need is what drives the capacity or the amount of pressure it has to develop and so on. But that's your flow, that's your pressure. If it's same with the pressure, if you can look at that and say, you know what, I think we could streamline this whole thing so that we could drop our pressure by about a third. Well, if you assume that you can do that at least the same efficiency as what it is now, or the best efficiency point, you can say, I think I could drop a third of my power off here. Okay. And then once you get into the efficiency, that actually gets a little bit harder, because it implies that you really do have enough test data there that you can say you know what the efficiency is. I mean, I can come up to a lot of fans out there just because I've been doing this for a long time and say, well, that particular fan, I know it's quite inefficient, and I know that there are better fans for that that'll take the efficiency from 65 to 85% or something like that. Well, that's an experience thing that comes into play there, but you don't need to get near to that far before you can already be estimating a bunch of these kinds of savings.
Great.
All right. Thanks, Vernon. I think we're a bit out of time. I think this has been really useful. Nick, do you want to wrap it up?
Sure. Yeah, I've just put up one other thing we wanted to mention before we wrap up, and this is if Sheriff is still on the call. What I was teasing at earlier off the top of this presentation, when you mentioned the 3 megawatt pump system that you're looking at, is a promotion of the fact that there is free expert support available through Save On Energy. So you can post your questions on the Energy Management Learning Platform discussion forum, and that will set the wheels in motion to get some feedback from experts, and could result in some coaching calls to help you. That would probably fit under the second box here, identifying and implementing industrial energy efficiency projects. So you can see the QR code on the screen. You can scan it now. You can see the email, or you'll get these materials and you can check it out then.
Perfect. Thank you.
Lastly, let us know what you think. Another QR code. So if you can scan that now.
The link's also in the chat if you want to click that.
Yes, thank you, Jay. In the chat, please click that. This is probably a great time to mention that this is the first in a series of webinars on this subject around estimating savings. So we're intending to go into other technologies, but also have the potential to go deeper into pumps and fans, perhaps in a webinar or other formats. So we'd really like to hear what you thought of this session, but also what else you would like to see in the future to build out this webinar series. Anything you would add to that, Jay?
No, I think that's great. And as Nick mentioned, this is going to be an ongoing series. We are looking to get some asynchronous material up on that training and support page of the Save On Energy website as well. So we'll be filling that out as the material is developed. And thanks everyone for participating. And as Nick mentioned, there is coaching advisory on industrial energy efficiency projects available. It's through the Energy Manager Learning Platform, and you can get access to that by registering for Energy Manager Support Services. This is provided through Save On Energy, and that link to register for that, if you haven't already, is in the chat there as well. All right,
wonderful.
Thanks.
All right.
Thanks, everyone.
We're a couple of minutes over time, so feel free to go have your lunch or go get ready for Halloween if that's what's next. But if you have a moment to type something in the chat, by all means, and we'll be sitting here for a few minutes. Otherwise, have a fantastic day, and thanks for attending.
You bet. Thanks.
Thank you, Vern.
Yep. Thanks, Nick. Thanks, Jay.
Thank you.